All right, today we are diving into a really clever engineering trick. It's a method that keeps everything from giant industrial turbines to the engine in your car from literally shaking themselves to pieces. It's called the trial weight method, and it is a fascinatingly precise way to solve the wobble.
You know the feeling, right? You've just thrown a load of laundry in, and suddenly the whole machine starts thumping and shaking so violently it feels like it's about to walk right out of the room. Well, that crazy shudder is the perfect everyday example of the exact engineering problem we're talking about today: imbalance.
So that wobble, it's not just some random thing. It actually has a specific name in engineering and a very clear cause. Let's break down what engineers really mean when they talk about imbalance.
Okay, think about anything that spins, a wheel, a fan, anything. Ideally, all of its weight is perfectly evenly distributed around the very center that it spins on. But what happens when one side is just a little bit heavier? Well, now its true balance point, its center of mass, doesn't line up with its center of rotation, and as it spins faster and faster, that tiny little offset creates a powerful force that yanks outwards. That is the vibration we see and feel.
So how on earth do you fix a problem you can't even see? I mean, you can't just guess where the heavy spot is and hope for the best. Instead, engineers use this really clever, systematic process. And this is the hero of our story today, the trial weight method. And this really gets to the heart of it. You could just guess, right? Stick a little weight here, a little weight there, and just hope you get lucky. But that's incredibly slow, it's inefficient, and you could easily make the wobble even worse. The trial weight method completely replaces that guesswork with a scientific, data-driven procedure that finds a precise, guaranteed solution every single time.
The basic idea here is just so simple, but so powerful. You use a variable you know, a small, temporary weight that you add yourself, to figure out the variable you don't know, the machine's hidden imbalance. It's kind of like using a measuring cup with markings on the side to figure out the exact volume of some mystery liquid. You use what you know to solve what you don't.
So how does this actually work in practice? Well, the entire method breaks down into a really logical four-step process that takes us all the way from figuring out the problem to a perfect solution.
So here's the game plan. First, you measure the problem exactly as it is. Then, you introduce one small controlled change. After that, you measure the result of that change. And finally, you use the difference between those two measurements to calculate the perfect, permanent fix. Let's walk through each one.
All right, step one is all about getting a baseline. You just run the machine as is and use special sensors to measure the vibration that's already there. You're looking for two things: its amplitude, which is basically how strong the shake is, and its phase, which tells you the direction of that heavy spot. This gives you the before picture. Now for the fun part, the experiment. You take a small, precisely measured weight, and you attach it to a very specific spot on the spinning part. And you know exactly how heavy this weight is and exactly where you put it. This controlled change is what's going to give you all the data you need.
Okay, with that little trial weight attached, you spin the machine up again. Now, the vibration will have changed. It might have gotten better, it might have gotten worse, but the key thing is that it's different. You record this new vibration, both the amplitude and the phase. This is your after picture.
And this is where the magic happens. By comparing the before picture and the after picture, engineers can perform a critical calculation. They figure out something called the influence coefficient. Think of this coefficient as a unique calibration for this specific machine. It basically tells you, for this much weight added at this exact spot, the vibration changes by this much. And once you know that precise relationship, you can use your very first vibration reading to calculate the exact size and the exact location of a permanent weight needed to perfectly cancel out that original wobble. It takes all the guesswork and turns it into a simple math problem.
Okay, so this is a really cool process, no doubt. But why do we go through all this trouble? Why does getting this precision balance right matter so much in the real world?
Well, the payoff is huge. First off, a balanced machine is a safer machine. It's not going to shake itself to failure. It's also way more efficient because it isn't wasting a ton of energy just fighting its own wobble. And maybe most importantly, it dramatically reduces the wear and tear on bearings and other parts, which makes the equipment last so much longer. In short, it saves money, it saves energy, and it prevents catastrophic failures.
So the next time you hear the high-pitched whir of a dentist's drill or feel the incredibly smooth power of a jet engine on a plane, just remember that invisible principle of balance.
This elegant little method of measure, test, and correct is quietly at work all around us, keeping our high-tech world running smoothly. It really makes you wonder, what other brilliant engineering secrets are hiding in plain sight?